this. Now, as usual, since the various discussion classes made different degrees of progress, I'll pick it up from the gathering that made the least degree of progress so that everybody gets the same treatment. After we finish our analysis of this system from a thermodynamic standpoint, remember, our interest regarding this system was, from thermodynamic data, calculate the composition of the system at equilibrium and see if we get agreement with the G-state graph that we have on page 8 in chapter 21. If you recall the G-state graph, it showed us, for example, that if we were to consider a system containing NO2 and N2O4 at normal laboratory conditions, 1 atmosphere external pressure, 25 degrees centigrade, 298 K, starting with either 2 moles of NO2 gas and 0 N2O4, or 1 mole of N2O4 gas and 0 NO2, that the equilibrium condition would develop, because that's the most stable thermodynamic state for the system. And the G-state graph said, on having started with 1 mole of N2O4, about 20% of it would decompose to produce NO2 gas. We started with the 2 moles of NO2, we'd get the same result. But to put this in perspective of decomposition of N2O4, if we look at the G-state graph, again it says, you start with a mole of N2O4 and initially 0 moles of NO2, about 20% of the N2O4 should decompose to get us to equilibrium. So let's see if our computations can give us agreement with that G-state graph. Here again is the equilibrium constant. There's the equilibrium constant value. The number comes from data in table 1, from which we can get delta H0R for this reaction as well as delta S0R for this reaction, and treat the data at 298 K to get delta G0 for the reaction. Then with delta G0 equals minus 2.3 RT log K, we get the log of the equilibrium constant, which from that calculation is a unitless number. But if we take the antilog, we get the number at 6.69. And we said, well, if we want units, from where do we get the units? You look at the equation for the reaction under consideration. That's the only way to get the units. And since we are using atmospheres rather than bar as pressure units, 6.69 atmospheres to the minus 1 units, atmospheres to the minus 1. So, our first course of action is, now that we have the equilibrium constant and we know the total pressure, we'll apply Dalton's law of partial pressures. Do you remember what Dalton's law of partial pressure says? It says 2 things, really. You did this in 2045. What are the things which Dalton's law of partial pressures tells us? The total pressure of or on a gas phase system is equal to the sum of the partial pressures of the components. Nothing fancy about that. So if the total pressure is 1.00 atmospheres, then the partial pressure of one of the component gases, because this is only a 2-component system, is the total pressure less the partial pressure of the other component. Nothing fancy about that. So I wrote this with respect to partial pressure of N2O4. Take this, put it in for the partial pressure of N2O4 and solve it. Nothing fancy, simple, first order arithmetic. 0.32 atmospheres for partial pressure of NO2 and 0.68 atmospheres for partial pressure of N2O4. And we would well expect before we did this calculation that the partial pressure of N2O4 has got to be greater than the partial pressure of NO2 because we know the system is far richer at N2O4. So, this is telling us at NLC, the ratio of partial pressures of the component gases is about 2.1 to 1. What's going to happen to this ratio if we study this system at higher temperatures? Will the ratio stay the same? Will the ratio get smaller? Will the ratio get larger? If we study this very same system at higher temperatures. You know, this is the kind of stuff I like to ask on exams, quizzes. Because it requires you to understand the system. Well, if I heat this system, at the instant of applied heat, does the equilibrium still exist? No. I disrupt the equilibrium. What reaction will take place to reestablish equilibrium? Le Chatelier. If I heat this system, am I going to break bonds or make bonds? Going to break bonds. So I'm going to get a reaction to get me back to equilibrium, which involves NO2 reacting to make N2O4 or N2O4 falling apart to make NO2. Which reaction occurs on heating? The decomposition of N2O4. So the system, as a consequence of heating, is going to get richer in NO2 and less rich in N2O4. Which means at higher temperatures, this ratio gets bigger or smaller? Smaller. The amount of this is coming down, the amount of this is going up. If I cool the system, ratio's going up. But if I want to study this system, I got to be careful about the temperature to which I cool the system. Because N2O4 liquefies at about 20 degrees centigrade. So I can't cool it too much. About 15 or 20 centigrade, I forget the date, but you can look it up. No, you got to keep stuff like that in mind when you play with systems. How does the system behave under the conditions at which you choose to observe it? Now then, keep in mind, we have a ratio of partial pressures, but we want composition. How can we get composition? In other words, when this system is equilibrium, if we started with 1 mole of N2O4 and 0 NO2, or 2 moles of NO2 and 0 N2O4, since we always wind up with the equilibrium mix, it makes no difference which way we were to start. Well, what will be the composition at equilibrium? Well, we'll have a mixture of NO2 and N2O4. How can we get that? Can we use PV equals nRT? Yes or no? Can we use PV equals nRT to get the system composition at equilibrium? This kind of stuff I like to ask. You know, if you give me a vote, I don't give a damn about the vote, even if the vote's right. You have to defend it. That's what matters. All right, let's draw a picture. And we'll draw a picture over here. I'm going to make a piston inside a cylinder. Do you want to start with the mole of N2O4 or do you want to start with 2 moles of NO2? It makes no difference. Which way do you wish to start? How many votes starting with the mole of N2O4? How many wish to start with 2 moles of NO2? And I gather that most of you don't give a damn, because most of you didn't vote. 1,000 points off. That's from the first question. Wait till I get to the second question. This is an exponential. 10,000 points off for the second question. Time you get to the end of this, you'll have a number that makes Avogadro look like a piker. Ha ha ha. All right, I got more votes for the NO2 stuff. Here we are. Initially, 2 moles of NO2. We're imagining we can do the experiment. What's going to happen to get us to equilibrium? The NO2 molecules will coalesce, react with each other to make N2O4. What's that do to the number of particles in the system? Does it keep the number of particles in the system constant? What does it do to the number of particles in the system? It decreases the number of particles in the system, right? Because every time 2 moles of NO2 react, I have 1 mole of product. So what's that doing to the volume inside this piston cylinder gadget? Volume going to stay the same? We got a free-floating piston operating at an external pressure of 1 atmosphere, and I'm reducing the number of particles inside this cylinder. So as the reaction occurs, this is coming this way. Now, I know that when it stops coming this way, the total pressure is still 1 atmosphere. The partial pressures are as we have calculated them. But we don't know the composition of the system. So at this point, we still don't know moles of either gas. And do we know the system volume? If we don't know moles of either system, of either component, if we don't know how many moles we got, even though we know total pressure and even though we know the temperature, can we know what volume we have if we don't know how many moles of stuff we got in there? Huh? So can we use PV equals nRT to get system composition? No! I've asked questions like this before. Students will say, oh yeah, I'll use PV equals nRT. Like hell you will. Not if you want to answer the question. But can I use Dalton's law of partial pressures? The second aspect thereof. You're damn right. That's what we have on the board. Because Dalton's law of partial pressures tells us that the total pressure of or on a gas phase system is equal to the sum of the partial pressures for the component gases. But Dalton's law also tells us that the partial pressure of a component gas is proportional to what property of that gas? On the board, I'll write a symbol for this property. I expect you saw this symbol in 2045. You see that symbol? What's that mean? What's it called? What's the name for that symbol? Greek letter chi. What does chi mean? That's what counts. If you're in Greek class, now you got a point. But this ain't Greek class. This is nasty Horvath chemistry class, where chemistry is what matters. What's chi represent? Nope.
Mole ratio.
Mole ratio. That's close. Mole what? You did this in 2045. Or maybe you didn't. I don't know what goes on in that class. Because every time I ask you folks about chemistry that you should have learned from that class, I get a bunch of blank stares. I don't know what's going on there. It's called mole fraction. You hear that? That term sound familiar? Mole fraction. What's mole fraction? It is a mole ratio, but a specific mole ratio where you're comparing moles of one component to total moles. Well, this is as simple as possible mixture, because there's only 2 components. So I wrote using Dalton's law of partial pressures. An expression which corresponds to the mole fraction of component N2O4 whose partial pressure is 0.68 atmospheres. Because if I take moles of N2O4 and divide it by total moles and multiply it by the total pressure, I'm going to get the partial pressure. That's what Dalton's law says. Well, how can I algebraically represent moles of N2O4 as well as moles of NO2 in the system? Well, if we started with 2.00 moles of NO2, that's what you wanted to do over here, that's what you told me, okay? Doesn't make any difference, you can start with the N2O4, who cares? If I imagine to have started this system, to develop the system from 2 moles of NO2 initially and 0 N2O4 initially. Well, at an equilibrium, I'm going to say, I got X as the representative of moles of N2O4. Big deal. So how much NO2 will I have at equilibrium? That's the $64 question from an algebra representation standpoint. Well, I started with 2.00 moles. How much NO2 has to disappear to make me X moles of N2O4? 2X! That's what that thing tells me. So I wrote that here. So I'll take this information, put it in here, find out that the mole fraction reduces to this. Oops, this goes away. Do the obvious algebra. How simple could this be? And here's what you get. 0.81 moles of N2O4 and 0.38 moles of NO2. Now keep in mind we said you'd get exactly the same composition for the equilibrium system if you started with 1 mole of N2O4 and 0 NO2, or 2 moles of NO2 and 0 N2O4. It doesn't make any difference. So if we imagine that we did do this experiment by having started with 1 mole of N2O4 and 0 NO2, we would wind up with 0.81 moles of N2O4 left after having formed 0.38 moles of NO2. Take a look at the G-state graph. How much of the N2O4 decomposed at NLC to get us to equilibrium? About 20%. You agree if we started with a mole and wind up with 0.81 moles, about 20% of it went away? 19% really. But it's pretty good. Okay? So we got it. Now then, the G-state graph also told us that you can start, or imagine to start, because again you can't do the experiment, because you're always going to have the equilibrium mix. But if you imagine to do this experiment by starting rather than with pure N2O4 or pure NO2, any mix of N2O4 and NO2, if it's not the equilibrium mix, a reaction will occur in the mix until you get to equilibrium composition, period, because that's the most thermodynamically stable state for the system. So, look at this equilibrium mix. Let's imagine that at NLC I make a mixture of 2 moles N2O4 and 1 mole of NO2. What's going to happen in this mixture? Anything? Is it equilibrium? This time I'm starting with more stuff. So what? Because the 0.81 moles of N2O4 and the 0.38 moles of NO2 tells me at NLC from a mole ratio standpoint, this system is at equilibrium when moles of NO2, moles of N2O4 divided by moles of NO2 at equilibrium is equal to what fraction? 0.81 divided by 0.38. At a glance, do you see that 0.81 divided by 0.38 is a number which is somewhat bigger than 2 to 1? Do you find this number comparable to what we got there? Doesn't it seem reasonable, Dalton, that the ratio of partial pressures has got to be equal to the ratio of moles? Isn't that right, Dalton? Huh? So if I start with 2 moles of N2O4 and 1 mole of NO2, what's going to happen? What's going to happen? All right, let's start with 4 moles of N2O4 and 2 moles of NO2. What's going to happen? Anything? Will a reaction occur? Is 2 to 1 equal to the ratio 0.81 divided by 0.38? No, it's close though. So if I start with this system, will N2O4 fall apart and become this? Or will these react with each other to become some of this? But will I get much reaction of these with each other in this system? No. Enough of this will react until I get a ratio of 0.81 to 0.38, which is about 2.1. Right? What if I start with this? Is that an equilibrium mix? So what's going to happen in this system? Now N2O4 is going to fall apart. Hey, once you know the system composition and the ratio of each system, the ratio of the components at the conditions selected, which for our case has been NLC, hey, you know what you're looking for. You will now know how any non-equilibrium mix of these two components must react to get you to equilibrium if it's not at equilibrium. All right? Question 2140 says, if Kp is 1.00 for this system, then delta G is 0 is 0. At what temperature will we be operating? Well, remember, we did this analysis at 298 K. And this number compares how to 6.69? This number's smaller, isn't it? So before you do any arithmetic to get this temperature, you know you're looking for a temperature which is higher or lower than 298 K. Higher or lower? Higher or lower? Because if that equilibrium constant value falls off to 1.00, what's happened to the partial pressure of N2O4 relative to the partial pressure of NO2? Is the partial pressure of N2O4 relative to the partial pressure of NO2 gotten larger or smaller? If the number goes from 6.69 to 1, the ratio got smaller, didn't it? That means the partial pressure of N2O4 got smaller while the partial pressure of NO2 got bigger. And to make that happen, you want to heat this system, don't you? You want to cause N2O4 to fall apart, don't you? So you already know you're looking for a temperature which has got to be higher than 298 K, because 298 K is the temperature at which we did this analysis. That's the chemistry. That's the stuff you always got to think about. That's where it's at. And that's the hard part, really. But that's where it's at. That's the chemistry. So you can look up the data for delta H sub F super 0 for the components and S0 for the components, and you can get these values and you get this temperature. All right, enough on that. Now here again is something which many of you got to look at yesterday, but some did not. I want everybody to get the same shape, the same deal. Perhaps you will recall, back in chapter 18, when we began to use at great length and on a regular basis the information in our acid-base table, and learn the definition of Ka, quantitative measure of acid strength, specifically to protonate water for the Ka values we have tabulated, because we're doing all our chemistry in water solution. We said at that time these Ka values for the strong acids, for which in our table there was only 4 listed beside hydronium. You had perchloric acid at the top, and then sulfuric acid, and then hydrogen chloride, hydrochloric acid, and then nitric acid. That was the order for which those 4 strong acids were listed immediately above hydronium ion. But we didn't give you the Ka values. All we said at that time is the Ka values are so large that practically speaking, those acids will be ionizing to the extent of 100% water solution. Well, let's see if we can verify that. Because now we have the wherewithal to do it. Because we've now become familiar with the ton of chemistry that's available in the thermodynamic properties data table. Table 1 at the end of chapter 20 once again. I'm considering Ka for the strong acid nitric acid. So I get out the data table. If I want to get Ka for nitric acid, then what I got to operate on is this. Here's the ionization reaction. And if I'm going to consider this ionization reaction at equilibrium, I'm going to have Ka. K for this equilibrium reaction is Ka for nitric acid, because it shows the acid in question reacting with water to make hydronium ion and, of course, the conjugate base of the reacting acid. Now here's what I need to use. I'm going to do it at 298 K. Use the appropriate R value, 8.31 joules per K mole. I go to table 1. I get delta G sub F super 0 for the components of this system. I find minus 80.7 for nitric acid, pure stuff, which at NLC is a liquid. And nitrate ion AQ, which is minus 108.7. A value determined by measurement relative to our thermodynamic reference standard for solution chemistry. Remember that? Formation of H plus aqueous has a delta G 0 value of 0 by definition. But I haven't here included delta G sub F super 0 for water, liquid, and hydronium ion. Why not? Why not? Because if I'm going to get delta G 0 for this reaction, I need to apply Hess's law to the sum of the delta G sub F super 0 values for the products less the sum of the delta G sub F super 0 values for the reactants. That's what Hess's law demands. But for what I have on the board, I've not written delta G sub F super 0 for water, liquid, and hydronium ion AQ. Why not? Why not? If I go to my data table, I'll find for water liquid, delta G sub F super 0 is minus 237.1. But I didn't write that down. Why not? What's delta G sub F super 0 for this thing? That's the same as delta G sub F super 0 for water liquid. Remember that fine point? Because for this reaction, delta GR is 0. Delta GR super 0 is 0. Well, since I know delta G sub F super 0 for this thing is by definition 0, the only way delta G sub R super 0 for this reaction can be 0 is if the thermodynamic properties for this thing and the thermodynamic properties for this thing compare how? They're equal. So in case you forgot that, that's why I made this point. So I don't need this stuff. That falls out in the wash when I apply Hess's law. So there's my delta G0 reaction for the reaction. And I get log K and I get Ka, and there's 8.2 times 10 to the 4th. Does that sound like a large enough K value to support the conclusion that if I make a nitric acid solution with water being the solvent, practically speaking, it's all going to hydronium ion and nitrate ion? Now then, under standard state conditions, I have this now. The Ka value, so I'll write this. You remember what conditions? Specifically concentration conditions must be established to define the standard state? What? 1 molar. So here's how I'm going to construct this system. In order to get this number, in the same solution, I imagine to have 1.0000 molar pure nitric acid, 1.0000 molar hydronium ion, the pH is 0.0000, and 1.000 molar nitrate ion. That's what I got. Water's my solvent. They don't have water included in this. This K tells me that for this system, starting initially in the standard state, to get to equilibrium, what's got to happen? Does the system stay there and look at you? Or does it react left to right or right to left as written? What happens? What's that K number tell you? Does this K number tell you that if I start this under standard state conditions, 1 molar, and 1 molar, it sits there? Is K equal to 1? No. Look at this K. So this is telling you, for this baby to get to equilibrium after I started at standard state conditions, it's going this away, big time. So I'll call it this. Here's what I started with. And the stoichiometry says, by whatever amount I increase the molarity of hydronium ion, I'm going to increase the nitrate ion molarity by the same amount. And this is going to be this. There you have it. You're going to solve this for x, all of which, this whole term is equal to 8.2 times 10 to the 4th. Tell me what kind of number you're going to get for x before you do any arithmetic. A number which is practically what value? 1. By golly. You're going to have to do this calculation to about the 5th decimal place before you find something besides a 0. For the molarities of this stuff. I mean, for the molarity of this stuff. In order to get a non-zero value for the nitric acid molarity in this system, you're going to have to take this to about the 5th decimal place. I wrote it down here someplace. I don't know. Well, I got this. You can play with it if you want. Because again, once we see the magnitude of this K value, it's screaming at us. The value for X is damn near the same as 1. And there's what I get for X if I go to 4 sig figs. Would you agree this is practically the same as 1? You'll agree with that. You want to calculate percent ionization for nitric acid in this system? Here it is. 99.95%. Hey, I'm taking that as 100% and I'm going. All right? Now then, you know how to get Ka for sulfuric acid. You write the reaction. Sulfuric acid, pure stuff, plus water, double arrows, hydronium ion, hydrogen sulfate ion. You get out table 1. You look up delta G sub F super 0 for pure sulfuric acid. It's in there. You look up delta G sub F super 0 for hydrogen sulfate ion AQ. It's in the table. You don't care about delta G sub F super 0 for water liquid, nor hydronium ion, because they're equal, right? Same as what we already did. And you go through this same rigmarole that we just did for nitric acid in order to compute Ka for sulfuric acid. If our acid-base table is listed in correct order of strength, what kind of Ka value are you going to get for sulfuric acid compared to 8.2 times 10 to the 4th? A bigger number. You can do the arithmetic. For sulfuric acid, if I've done my arithmetic correctly, I get this tiny Ka value of 3.6 times 10 to the 11th. You think it's fair to say sulfuric acid ionizes 100% when you put it in water? You betcha. Now then, again, if our acid-base table is correctly composed in regard to order of relative strengths, what kind of Ka value am I going to get for HCl relative to the Ka values we have now looked at for nitric and sulfuric? The Ka value for HCl will be bigger than that for nitric and smaller than that for sulfuric. Just for fun, how many of you got to look at this calculation yesterday? Well, then a lot of you didn't get to look at this calculation. Because you see, when you're going after Ka for HCl, now you've got a greater problem. A more challenging problem than what we've had here. Why is that? HCl under normal laboratory conditions is a gas. So how are you going to talk about it in terms of molarity? Because we're going to write this. Now you know how to get the K value. That I should, maybe what I said suggested to you that calculating the Ka value is difficult. No, that's not difficult. What's difficult is calculating system composition at equilibrium. Let's write down some information and then we'll pick it up from this point next time. You'll get Table 1 information. So let's extract delta G sub F super 0 for HCl gas, which is minus 95.3. And the other part of the puzzle is this. All right? So with this, calc Ka HCl. Just like we did there. But the tickler is, what shall we do to get a handle on this at equilibrium? Because this is a gas. Whoop. Whereas what I'm concerned about is how much HCl will be in this HCl solution that has not reacted. How much unreacted HCl will be present at equilibrium? For nitric acid, we showed you that it's damn near nothing. It's 1.0 less this number. You know how to play the game for sulfuric. So let's see if you can figure out how to play the game for HCl. And for this, for those of you who didn't do this, I'll give you this clue. You're going to have to use this, because I don't want to fool around with van der Waals corrections for HCl behavior. And we'll pick it up from this point next time. And start right now to take a look at the first few pages of Chapter 22 on electrochemistry, because we're into that on Friday.